Hello everyone, welcome back to my Chem Corner. So in this video, we're going to do another topic from solid state, which is imperfections in solid. In case you're new to this channel, please don't forget to subscribe and hit the bell icon so you receive further notification as and when I upload my video. So let's move into the topic, which is imperfections in solid. So here, when we've learned about crystalline solids and amorphous solids, these imperfections, as the name says, are observed in a crystalline solids. So here, crystalline solids, we've learned that they have a short range as well as a long range order. But in general, these crystals don't have a perfect structure. They are not in perfect geometry. But why does this happen? There are two reasons to it. These will happen either due to the presence of impurities or in case there is a dislocation of any constituent particle from their position. So these are the main two reasons why there are some imperfections in solid, or crystals don't have a perfect geometry, or even if they have a perfect geometry that could be disturbed is due to this. Now, when does this happen? When does this all impurities are there, or when does this dislocation of impurities, dislocation of constituent particles taking place? These are possible when we do crystallization. Each type of a crystal, when you try to do crystallization, they take their own time to settle. But when we do crystallization on a faster pace or on a moderate rate, what happens is these imperfections in solids are seen. Say, for example, when we try to suddenly cool something, you might find a hollow in the center, you might find some air space in center. This happens even if you're doing a normal cooking in the kitchen. When we say, for example, you're trying to bake or all of these, what happens is if you don't do it properly, you might find some hollows in between, you might find some air spaces in between. It's the same thing in case of crystallization when you look at solids too. So when it's done on a faster pace or on a moderate rate, what happens is you might find these imperfections in crystals. So what is the definition of an imperfection in crystal or a crystal defect? Any deviation or departure from perfectly ordered arrangement of a constituent particle in a crystal is called as a crystal defect or an imperfection. Crystals are supposed to have its respective geometry, its respective arrangement of constituent particles. If there is a deviation from all that, if the shape is changing, if the geometry is changing, if the arrangement of these particles are changing, then they are classified under crystal defect or an imperfection in solid. So depending on the type of an imperfection, there are different classifications under it, whether they leave the crystal lattice or are they going and sitting somewhere in between, they will be classified differently. So let's look at the classification. So here we have different types of crystal defects. One is called as point defect and the other one is called as a line defect. Now what are these called as? What do they mean? What is a point defect? What is a line defect? Just go by the terms. In this case, point defect, you're talking about a particular point or a particular atom in a crystal. It is showing irregularities or deviation from an ideal arrangement around a point or around an atom in a crystal. That is called as a point defect. And the same way, if you're talking about a line defect, you are talking about an entire row of lattice points. So if there is a change in or if there's a disturbance in the arrangement over an entire row of a lattice points, then they are classified as line defects. So if you go by the term itself, you get what the meaning of these defects are. Now what are we going to concentrate on? What are we going to go in detail and learn? We are only going to focus on point defect. We're not looking at line defect. We're going in detail with respect to point defect. So here point defects are broadly classified into three types. The first one is stoichiometric defect, second one impurity defect, and the third one is non-stoichiometric defect. Let's go by the term itself. Now stoichiometric meaning you are not disturbing the stoichiometry of that particular crystal. The stoichiometry remains undisturbed, or the ratio of number of particles remain undisturbed. These are also called as intrinsic or thermodynamic defects. They have other terms also. Now, what about an impurity defect? Impurity defect is when you have an impurity. Another, say in an NaCl crystal, you're going to have a strontium metal. That's called an impurity defect because you're having an entirely different cation in that particular crystal. So that is broadly classified as impurity defect. What about non-stoichiometric defect? Now, non-stoichiometric defect is going to talk about those defects where the ratio is going to be disturbed. It's right opposite to a stoichiometric defect. Now, under stoichiometric defect, we have 4 types of defects. We will go in detail for each one of them separately. We have vacancy defect, we have interstitial defect, we have Schottky and Frenkel defect. We have 4 different types of defect for which we will go in detail in upcoming slides. Now, as I told you, non-stoichiometric defect, the stoichiometry is disturbed in this case. Alright, so maybe you have another metal going to be replacing a particular metal, then the entire stoichiometry is going to be different because sometimes you might have an incoming metal with a different valency. In that case, probably you might have an introduction of an electron there, or you might have a vacancy there. So it's all going to be disturbed completely. That is going to be classified as non-stoichiometric. There is no stoichiometry. That's what it means. Now, non-stoichiometric defect can be classified as 2, metal excess defect and metal deficiency defect. So, like I've told you, if you have another metal coming in picture in that particular crystal, you can have a metal of a different valency. In that case, you're going to have a metal excess defect because in that particular crystal, you're going to have more number of metals right now. If you're talking about metal deficiency defect, you could have a removal of a metal probably, but you might have say an introduction of an electron in that case. So what happens there is that you're having deficiency of a metal, right? So these are the 2 types of non-stoichiometric defects. One is metal excess defect, the other one is metal deficiency defect. Now, under metal excess defect, we have 2 different types. One is caused by anionic vacancy and the other one is caused by excess cations. So each of these we're going to go in detail and we're going to learn what are the properties of it, how does it happen, and which type of examples are these type of defects generally seen. So we will go in detail in this video. Now the next one that we're going to talk in detail is about stoichiometric defects. So let's learn about that. Now under stoichiometric defect, we learned 4 types. We learned about vacancy defect, we learned about interstitial defect, we learned about Schottky defect, and we learned about Frenkel defect. Now under vacancy defect, just as the name says, you have a perfect crystal here. Alright, there are all atoms, or there are all these lattice points here. But what is happening? In this case, one of the atom is moving out. So what's happening there? There is a vacancy here. There is an empty space here. So that means the point or that particular atom is missing. So when some of the lattice sites are vacant, the crystal is said to have a vacancy defect. So there are chances where these happens, right? When you do sudden crystallization, maybe one lattice site could go missing. It could go out of the crystal. In that case, it will produce a vacancy defect. Now, because this is happening, it's moving out of the crystal, the mass of that particular crystal is going to reduce. It's just like we have a class of students and there's one student who's pushed out of the classroom. So what is happening there? The number of students in the class is going to reduce. The strength of the class is going to reduce. Same thing here. When there is a lattice site that is vacant, which means that particular point or an atom is missing, the mass is going to reduce. When the mass reduces, the density of the crystal is also going to reduce. Now, when is it mostly seen? When heating of the crystal is done. When you start heating them, these metals can, or these points can go missing. Alright, so it's just a basic thing where when you heat, there is a lattice point that's missing, it moves out of the crystal and a vacancy is produced there. Now when this happens, the mass is going to reduce and the density of the crystal is also decreasing. So that's the first type of a stoichiometric defect. Now let's move into the next type of a stoichiometric defect, which is the interstitial defect. So here, as the name says, you have a perfect crystal here, same thing. But what are you observing here? Probably somewhere you have a cation which is of a smaller size. It could occupy the interstitial site. So say for example, whenever we make students sit in class, there are spaces in between two rows of students or between each student. So what happens if there is a small child in the class? The child can fit in those small spaces. The same thing here. The cations are there. Cations are generally smaller in size. So what happens is when you try to heat the crystal again, what will happen is these smaller cations can fit into these smaller spaces in the crystal. These smaller spaces in the crystal are called as interstitial site. So the particle is going to occupy the interstitial site. So in this case, what is happening? Because there is a cation that is introduced into the crystal lattice, the mass is going to increase. When the mass increases, the density of the crystal is also going to increase. So vacancy defect and interstitial defect are quite opposite. In the vacancy defect, a lattice point moves out of the lattice. But in interstitial defect, a cation can come and sit in smaller spaces in between these lattice points. So they are quite opposite to each other. Now, these vacancy defect and interstitial defect, where are these generally seen? These are generally seen in those type of solids which are non-ionic. So they're seen in non-ionic solids. But what type of defects are generally seen in an ionic solid? The remaining two types of defect, which is Schottky or Frankel defect. So the vacancy and interstitial defects are observed in non-ionic, whereas Schottky and Frankel are observed in ionic solids. So now let's move into the next type of stoichiometric defect, which is the Schottky defect. Now in Schottky, I have a perfect crystal here. So if you see these orange dots, they are all cations, and these gray dots are all anions. So when you see the next picture over here, what do you see missing? From this point, you see that a gray dot is missing or an anion is missing. And over here, you see that a cation is missing, which is the orange dot. So here we can conclude that a cation and an anion both are missing from the lattice so that they maintain electrical neutrality. Now, this is a condition observed in a Schottky defect. So you have a cation and an anion both missing from the lattice points, which will result in electrical neutrality. Now when this happens, because the cation and anion both are missing from the lattice points, the mass of this is going to reduce. And when the mass reduces, the density should also reduce. Now in which type of ionic solids are these observed? When the cation and anion are of comparable sizes, those type of ionic solids, the Schottky defect is observed. So I've given you a few examples. You can choose any one of it when you're writing an example. You have sodium chloride, potassium bromide, cesium chloride, and silver bromide. These are observed in these ionic solids. Alright, now the next one is Frankel defect, which is the last one under stoichiometric defect. So here when you see, you have a perfect crystal, but in the next diagram, what do you see? There is a vacancy here. What is missing? The orange dot is missing. Where has it gone? It has gone to some interstitial site here. So what is happening in this case? The anions, when the cations this arises when the cations will occupy interstitial site instead of moving to completely outside the crystal. So here what happens is you are finding a dislocation defect, because here the cation is getting dislocated from its normal site and it's moving to some interstitial site. So you observe an interstitial defect here. But in this case, you can also observe a vacancy defect because there's a vacant site here. So in Frankel defect, you can find both. You can find a vacancy defect. You can also find an interstitial defect. But what about Schottky? You can only find a vacancy defect. Now in this case, when you compare and see, is this particular cation that was here moving out of the crystal? No, it is in the same crystal itself. So what happens? No ions are missing. They are only getting reshuffled, right? It's just moving to an interstitial site. So in this case, the density remains unaffected. Okay, the density is unaffected in this case. Now, what type of ions are they observed? In those ions whose cation and anion have a large difference. They need that difference, only then the cation can sit in the interstitial site. If they are of comparable sizes, what will happen? The size of the cation and the anion will be similar. So the cation cannot really sit in the interstitial site. So in this case, you should have cation and anion which differ in a large difference. Example here is zinc sulfide, AgCl, AgBr and AgI. These cations and anions have a huge difference between them. Now if you observe these examples, silver bromide is one of those examples that were there in both Frenkel and Schottky. That means to say that they observe both of it. Why is that so? It is only because the radius ratio is an intermediate. They are not too small. The difference between them is not too large also. They are intermediate. So what happens is they can show both defect. They can show vacancy and they can show an interstitial defect. Both Schottky and Frenkel is observed in case of AgBr. That is one of the questions that they can ask for a mark in the exam. Why is AgBr observing both defects? It's only because the radius ratio between Ag and Br is intermediate. They're not too small, they're not too big differences. So this is about the Schottky defect. Now when you learn about the Schottky defect, one common question that can be asked in the exam is differences between Frenkel and Schottky defect. So what are you going to do? Just write the summary of this in a table. And that's exactly what I've put down here, the differences between Schottky and Frenkel defect. So under Schottky and Frenkel defect, the very first one that can be written here is, you can write the definition between them. Schottky arises due to missing of cations and anions and hence maintaining electrical neutrality. Frenkel defect you can write when the cations occupy the interstitial site than the normal site. When you look at a Schottky defect, you can say that they observe a vacancy defect, whereas Frenkel defect has interstitial defect. Now in Schottky defect, because both cations and anions are missing, the density is going to reduce. But in Frenkel defect, because it's only moving to an interstitial site, the density is going to remain unaffected. Now under Schottky defect, these are generally observed by cations and anions of comparable sizes, whereas in Frenkel defect, they need large differences between cation and anion. So these are a few differences between Schottky and Frenkel defect when asked in the exam. Never give examples as a point of difference. They are not a point of difference. You're not trying to tell any difference between them when you are giving an example. Examples are only given when asked in a question, not in a difference. Alright, so that was all about Schottky defect. We will now move on to the second type of a point defect, which is called as impurity defect. So as the name says, it is due to an impurity. Alright, so here let's see how that happens. So here I have a crystal. In this, if you see, it is basically an NaCl lattice. But what is the impurity in this? Strontium. If you see here, Sr2 plus is the impurity. How does this happen? When does it happen? All this is what we're going to learn under this. So here, you're going to consider crystallization of a molten NaCl in the presence of small amount of SrCl2. When you do crystallization in the presence of it, what will happen in this case? Some of the Na plus ions can be replaced by Sr2 plus because it's happening in the presence of SrCl2. Some of the ions here is going to get replaced with strontium ions. Now what happens is when you try to replace them, if you observe their valencies are different. Na is with a +1, Sr is with a +2. So to maintain that electron count or the electrical neutrality, what will happen is because Sr is with 2+, you need to replace 2 sodium ions. 2 sodium ions should be lost to accommodate 1 strontium ion. Now when you do that, what will happen? there is a cationic vacancy that is observed. Right? One of the sodium ions is occupied by Sr2+, but the other place is going to be vacant, and that is going to be a cationic vacancy. So in this case, what is happening? The number of cationic vacancy produced is equal to the number of strontium ions that is introduced. If you have introduced only one Sr2+ ion into the crystal lattice, you will have only one vacancy. If you have introduced two strontium ions, then you will have two vacancies. So this is only due to an impurity in the crystal lattice. So that is all about impurity defect. Now the next one is the third type of a point defect, which is a non-stoichiometric defect. Under that, the first one is a metal excess defect. So as the name says, it is due to an excess of a metal in the crystal lattice. So here, let's see how to do this. The first one under metal excess defect is going to be bianionic vacancy. A metal can be excess if an anion can move out of the crystal. Okay. So here again, we're taking a classic example of sodium chloride. When sodium chloride crystals are heated in a sodium atmosphere, what will happen? Sodium ions are going to accumulate on the surface of this crystal. Now when sodium ions are going to get accumulated, what will happen? Some of the chloride ions are going to move to the surface. So when that happens, the accumulated sodium atom will lose an electron. So whatever sodium atom is there at the surface, it will try to release an electron, and it will form sodium plus ion. Now when that happens, whatever Cl minus comes out of the crystal, it is going to form NaCl with that sodium atom. Now what happens to the electron that's released by the sodium? It is going to take place. It is going to be sitting in the place where that anion came out. So it's going to be entrapped in the anionic vacancy. Therefore, the crystal will have excess of sodium. Alright, because one Cl atom has moved out, now it will have excess of sodium atoms in them. Now the anionic vacancy that's containing this electron has a particular name, and that's called as F center, or it's called as Farben center. Now what is the responsibility of that electron? What is the point in that electron being there? When we do salt analysis in practical in first year, what did we observe? When we do any salt analysis procedure, we always do a flame test in the group 5. Now in that, when we do, we always see a flame test in the confirmatory test. How is that coming? It is because of this particular electron. When the salt is heated, the electron is going to undergo excitation, absorbing some visible region. Now what happens? Because of that, it's going to result in a flame color. That is why sodium when heated will give you golden flame, golden yellow. Potassium gives you a lilac color. When you heat your calcium, it gives brick red. Strontium gives crimson red. Barium gives apple green. It's because of that particular electron undergoing excitation. So this is all about metal excess defect due to anionic vacancy. Now the next one is the same one, metal excess defect by the presence of an extra cation in the interstitial site. So here when we look at zinc oxide, when you look at it room temperature, what is the color? It's white, right? But when you heat it, what will happen? It is going to lose an oxygen atom. So here I take zinc oxide, and when I heat it, it's going to have zinc 2+ with the release of electron, and oxygen is formed. Now what will happen? There is excess of zinc 2+ in the lattice. The excess of zinc 2+, where is it going to go? It will move into the interstitial site, because zinc is a metal, a cation. It's a smaller size. So it's going to move into the interstitial sites and electrons to the neighboring interstitial sites. Now when this happens, there is excess of zinc in the crystal. And those electrons which move to the neighboring sites is undergoing excitation, and therefore zinc will now give yellow color when it is hot. So in this equation, this zinc is going to occupy the interstitial site, the electron that is here is again going to give you color of this to the flame when you try to heat. That is why zinc oxide at room temperature is white, but when it is heated it gives you a flame color yellow. It's because of this entire process. Alright, and now we have the last type, which is metal deficiency defect under non-stoichiometric defect. So here if you see, this defect is observed in metals exhibiting variable valency. So in your periodic table, if you think about those metals which exhibit variable valency, where are they observed? They are observed in the D block elements, right? Where you have your transition metals. So in this case, if you're looking at an example, you're taking a crystal FeO, iron oxide. So in this case, in iron oxide, some of the Fe2 plus is missing from the lattice, and their positions are occupied by required number of Fe3 plus ions to maintain electrical neutrality. So when Fe3 plus ions, which has higher valency, is occupying Fe2 plus ions, what is happening? Naturally, there is a lesser number of cations. So in this case, you will observe that the less amount of metal is present, which is needed to maintain stoichiometric proportion, right? So there you have metal deficiency defect observed. So here some of the sites of Fe2 plus are occupied by Fe3 plus, which is of a higher valency. So generally when this happens, you will have lesser number of ions, or you have metal deficiency defect observed. So these are a few defects that you see when you look at a crystal and when you study them in detail. Depending on what type of a crystal that you take, you will find these many defects in it. So I hope this video has been helpful for you. If you have any suggestions, kindly drop it in the comments, or you can send me an email in the email ID in the description box given below. I'll see you in the next video. Stay connected. Thank you so much for watching.